I know you're all wondering why I called you here today. As you know, our dear friend, Mr. Pink, was murdered recently, and we are attempting to find the perpetrator. I have brought you all here to state the evidence. Mr. Quincy.
Ah, yes, thank you. Saturday morning at 5 o'clock, a Miss Peterson found our dear Mr. Pink along the side of the road in the position you see now. At 6, I had my team measure the sodium ion, lysine, and cadaverine concentrations in Mr. Pink's blood in order to determine his time of death. For those of you who have not learned this, as the body decomposes, the sodium and lysine concentrations will decrease at a set rate, and the cadaverine will increase at a set rate. From this information, my team determined when Mr. Pink would have been killed to the closest minute. Interns?
We began the process to determine the time of death by first plotting the data of the time versus sodium concentration and the time versus lysine cadaverine concentration. Figure 1 shows both the relationship of the time versus sodium ion concentration and the lysine cadaverine concentration. It illustrates the correlation between time and sodium concentration. By determining the linear equation of the dataset, we were able to extrapolate the sodium concentration at time 0 and the rate constant. The linear equation, y equals mx plus b, is drawn from the integrated rate law for a zero-order reaction. The order of our reaction for the sodium ions was given as zero order with the data. The initial concentration was given by the y-intercept, and the rate constant, k, was given by the slope.
Figure 2 demonstrates the relationship between time versus concentration of lysine and cadaverine and the relationship between the rates of reaction of both lysine and cadaverine. When both data sets are plotted on the same diagram, it illustrates the time is inversely proportional to lysine and directly proportional to cadaverine concentrations. In other words, as time passes, the concentration of lysine decreases while the concentration of cadaverine increases. Because lysine is carboxylated into cadaverine, both lysine and cadaverine concentrations level out to a point in which they have reached equilibrium. This means that only the lysine concentration reaches a point where it can no longer be converted into cadaverine. The cadaverine can no longer be formed because there is no more reactant to form the product. Although the two seem to be the same order, further research indicates that lysine is first order and cadaverine is second order. Figure 2 shows the zero order of the concentrations of lysine and cadaverine, where the raw data is graphed and there's no manipulation of the numbers yet. Figure 3 and 4 show the first and second order of the data, respectively, where the natural log of the concentration is taken and 1 is divided by the concentration. In showing the data in this manner, it shows the order of the reaction. If a graph is more linear in figure 3, then that means it is first order, and if a graph is more linear in figure 4, then that means it is a second order reaction. First orders are linear during the natural log of their concentrations, and second orders are linear during 1 divided by their concentrations. By looking at figure 3 and 4, the reaction from lysine and cadaverine is first order, as the line of lysine is more linear in figure 3, and cadaverine is second order, as is more linear in figure 4.
In the calculations, we used the rate law and the integrated rate law to determine the rate. The rate was needed to find the rate constant, which was used in the integrated rate law to find the time of death. Using the sodium concentration data, the reaction rate was determined by using the zero-order rate law. To prevent any inconsistencies, the rate was used at 2 significant figures, or 0.39 millimolarity per hour. Then, the constant and the rate were plugged into the zero-order integrated rate law to find the time, 11.44 hours. This means he was killed at around 6:34 p.m. the previous day, or 11 hours and 26 minutes from 6 a.m. By using the given lysine concentration, we determined the time of death to be around 7:06 p.m. though. We determined this by observing the graphs of the concentrations of lysine and cadaverine. Figure 3 shows that lysine is first order, and figure 4 shows that cadaverine is second order. After determining the order of the lysine reaction to be first order, we use the first order rate equation to figure out the rate constant. We put the given concentration into the equation, and we're able to determine the time of death by using the integrated rate formula. At this point, we found the time of death to be 10.91 hours before he was discovered, making the time 7:06 p.m. With the difference between the two times, we took the average of both, concluding that Mr. Pink's death occurred around 6:50 p.m., or 11.10 hours before the discovery.
From this information, we have discovered that Christina cannot be a suspect because she had SI for biology at 6 and was nowhere near the scene of the crime.
Rain's DNA was found at the crime scene. This led the police to believe that she could be the perpetrator. But if anyone knew her, they would know that she works as a tree cutter and was working on a tree at 5 p.m. She got cut, and that would make the DNA older than the crime scene.
Then there's Maddie. It's highly possible that Maddie was at the scene of the crime, and she shows reason to commit this crime. You and Mr. Pink had differing political views, right?
Hell yeah.
As well as that, you recently purchased a gun, correct? What I do in my free time is none of your business. It would be safe to assume that Maddie is the perpetrator.
Except for one thing. A cricket was found at the crime scene, and it saw everything. It chirped a Morse code and kept on spelling the name Q-U-I-N-C-Y.
Of course! It all makes sense! Why else would you force all these interns to come out here and do their work, knowing full well that they would make mistakes?
That's ridiculous.
Not to mention, Mr. Pink was always Quincy's rival, and Maddie's gun recently went missing.
Isn't Quincy off on weekends?
Quincy out! And I would have carried away with it if it weren't for you meddling kids and your damned crickets!